This is the start of the presentation. Welcome to the workshop, which is Generative Adversarial Network. And to make a long story short, this is one of the neural networks which a lot of it's getting a lot of hype today, which is why I'm presenting. But before that, let me just go through the agenda for today. So first of all, I'm going to introduce certain background knowledge since, for example, neural network and how they generally learn, and then I'll just introduce you what's what GAN is about, as long as why we have this GAN, one of the motivation, which is perturbation, and then I will look briefly into the applications, which is cycle GAN and also style GAN. So first of all, what is a neural network? So neural network, you can think of it as a function. As if you look from this if you look from this picture, you can see that let's say you have an input image which looks like a 7, and you pass into a neural network, and therefore you hope that this neural network will tell you that, hey, this image is a 7. But what it actually means is that it is a composite function. So from the one before, you can see that why it is a function. But the reason that it is a composite function is that each of the new let me rephrase. It is composite because it has a lot of layers, and each layer kind of depend on the previous layer. So you have like a lot of the relationship being concatenated to each other. So what does this mean? So to understand what I just said, we see that from this picture, each neural network has a lot of neurons, and these neurons are being laid in different layers. So let's say this is the first layer, which is also called as input layer. Second and third are hidden, and the last one is output. So this hidden layer output depends on the input, and this blue layers in output depends on the input from red, and finally the green depends on the blue. And the value of each neuron also depends on the weight of the connections, because you can see that the neurons in each adjacent layers are being connected to each other, and the weights will dictate how will the input influence the output values. And of course, there's also this activation function, which I won't talk too much about because this is not really a neural network workshop. And this picture is just to show you how deep a neural network could go. And since neural network is being used a lot in machine learning, that we kind of also need to know how neural networks learn. To keep things simple. We'll talk about things in the context of supervised learning, meaning that whenever a neural network predicts something, it will also get the answer, which we also call the label, and then from there it will learn how to adjust its weights in order to make a better prediction. So pictorially, it means that, let's say the initial weight is here, and then this j is the cost function, where cost is kind of like a sign of error that tells you, okay, how much off you are from the desired output. Then it will adjust its weights in the fashion that it will decrease the error, and eventually, hopefully, it will reach the global minimum, which is the best possible thing that it can predict. To make this into pseudocode, what happens is that for each sample, it will make an initial prediction, which is indicated over here, and then it will get a label. So, for example, let's say if in this picture it looks like a 7, and initially it might predict something as 5, and then we tell them, okay, this is wrong, and then it will find a way to compute its sorry, it'll find a way to compute its error in prediction, which we call it as E, and then we will will calculate, right, for each of the weights, which of the parameters that that the neural network can learn from and adjust. How what is the derivative of E with respect to W? So this, it kind of involves a bit of calculus, and then we want to update such that it's update the weight such that it goes opposite to the direction of DEDWs, and this alpha term here is like it's what people call as learning rate. But basically, the idea is that we want to move all the weights together in the hope that the training error will decrease. And we do this for different training samples, and for each of the samples, we do this many times. And so like let's say like 100 to, or even sometimes thousands of times. It's in the hope that the neural network will be able to predict something properly in the end. Now, for the purpose of this workshop, let me also tell you that the types of neural networks models. What I tell you just now, like give you an image and ask you to tell me the number. This is called discriminative network. So discriminative means that you want to you have a neural network and then you want to predict or classify. So classify means that give you a number and then you probably predict somewhere between either 0, 1, 2, or all the way until 9. Predict means that let's say I give you certain I give you like let's say let's say I give you the attributes of certain person, and then you predict how much does this person earn every month, for example. So that is called prediction. The thing that is more interesting is generative, which still receives a lot less attention compared to the discriminative networks today. But basically, what happens is that given you have a model and then you want to generate certain examples, and these examples have to follow certain distributions that you like. Why is it important? You'll see later. Now let's also tell you about let me also tell you also about what's neural networks, what's the issues surrounding neural networks are. So the reason why people use neural network is that it is very powerful and it seems to be able to predict a lot of functions well, as long as you give the neural network enough training, enough resources, and enough samples. But the problem is that for these neural networks, if you are not careful enough, it is very vulnerable towards perturbations. So, for example, let's say you have corrupted inputs, where someone just perturb the input by a little bit, that can cause the neural network to predict something that is drastically different, and this can have disastrous consequences. So one thing that I could imagine is that, let's say you have a self-driving car, and the self-driving car learns to recognize, like let's say the signboard or the traffic light in order to know what's the status and know what's the next step. Suppose that you change the scenery by just a little bit, like for example, it's you train your self-driving car on a sunny day, and suddenly it rains, and you are driving the self-driving car. It might, in the extreme case, it might just interpret green as red light as green light, and your self-driving car is screwed up. So that's how serious it could be. And a lot of the deep learning framework focus on the discriminative part, meaning the prediction part. And this is because generative network is generally hard. And one way is that because we want to generate something, and generation is it's not like discriminative where someone can teach them that, okay, this is a label, and then you want to predict, sorry, this is the image, you want to predict this is what you need to predict. For generative, it's a bit hard, where you kind of need to learn a bit of the statistical statistical properties, and also the distribution of the things that you want to predict. And this is generally harder than just the prediction. So let me detour before I go into what GANs is. Let me just tell you one of the motivations behind behind GAN, the generative adversarial network. And this is how easy it is to corrupt the input data in order to screw your neural network. So of course, the motivation here is to tell you that input perturbation is actually easy. So let me I'll just describe how how are we going to do it. So going back to this this example here, what happens is that let's say this is the neural network that we know that okay, it's doing well. Given this image, it will predict a 7. Then then what happens is that we want to perturb we want to perturb the input, but so how are we going to do it? So for each of the pixel over here, we look so for each of the pixel over here, we see like what is the different the partial the derivative of the error versus, with respect to this to this pixel. And then we move the pixel in the direction instead of the opposite of the direction just now. We move the pixel in the direction of this of this derivative. So the goal is to increment the error. So to clarify well, when the neural network learns, it want to adjust the weight in order to minimize the error. Now we want to adjust the input in order to maximize the error. So I'll just show you this example. This is actually taken from my assignment last year, and yeah, like it's like we have the right code. So for the assignment, so for this reason, I'm not showing you the code, but I can kind of show you the results, which is that we have this MNIST digit in the this over here, and then you can put and then this is how much you perturb, and honestly not much has been perturbed. Maybe the background changed a bit, and yet the neural network will just predict something different. So let's say this is 0, it will predict that it's a 2 with a 91% confidence, which is very very surprising, right? And then you can see that this is the original number, and then it will just predict something. It will just predict something else. Okay. Let me see. Is there any question until now? Okay. So the next thing I want to talk about is is to actually talk about what the GAN is, Generative Adversarial Network. Let me just show you some important part of the clip. Okay, so this is the gist of of GAN. So GAN was invented by a group of researchers, including Ian Goodfellow, and all of them are from University of Montreal. And this is a network that combines both the discriminator and generator, and both of them have competing objectives. So the discriminator task is to differentiate between real and fake samples, and the generator task is to generate samples in order to confuse the discriminator. So one way you can think of it is that, for example, our cache is produced by, I think it's called the Central Bank of Canada. I'm not sure what's the name. And we know that we are not supposed to produce fake money. But let's say let's say one day we got curious and we want to know, okay, how can we produce money? The initial chances are that the moment you try to produce money or print money, everyone will know it's fake, and then so you think, okay, how I can improve my money producing skills such that people won't identify that it's fake. Then you keep practicing, and finally one day the Bank of Canada couldn't differentiate between the money you produce and the money they produce. And then one day, Bank of Canada notices that, okay, that someone has been producing fake money, and then they want to upgrade their systems of discriminating. So and then you know that the Bank of Canada is being better in discriminating between their money and your money, and then you keep improving. So this cycle goes on and on. I'll show you more the examples in a more detailed manner later, but this is just a high level overview. So to show you to give a more pictorial explanation, so let me just say that these images are actually from the same YouTuber that I shared to you just now, and I guess I should find a way to give him the credit for this. But let's say our real samples are so-called standard faces. So what standard faces means in this context is that if you look at the first and the top left and the bottom right corner, they should have high pixel value, and which also means that they should which is basically black, whereas the ones at the top right and the bottom left they should have low pixel values. And what happens is that what happens is that the discriminator wants to be very good in categorizing this as this type of things as faces and this one as noise, whereas the generator wants to produce something that looks very similar to these faces. So let me so here's a bit of background knowledge, which is called the sigmoid function. You don't really have for this presentation, you don't really have to know a lot about this what this probability does. This sigmoid function does. All you need to know is that it is a function that maps the whole real space into 0 to 1. It is increasing, and then sigma of 0 is 0.5. Sigma of very, very small is 0, and sigma of something very, very big will go very close to 1. It won't be 0 or 1 exactly, but it will be very close to these values. Now let's first suppose that we have this discriminator network, and these are the weights. So how would you know? How did I get the answer 0.73? Let me just walk through with you this example. So this is a real face because and in fact the so-called pure face for this purpose. So this is the top left is 1, the bottom right is 1. The other two are 0. So what happens is that suppose our weights are also in this form where it's +1 for this, -1 +1 for this, and don't forget for neural network there's also a so-called bias term. So bias term always have it's always like a dummy input of 1. So how do you come up with this one? You do 1 times +1, which is 1, 0 times -1, which is 0, 0 times -1, which is 0, 1 times +1, which is 1, and 1 times -1, which is -1. And you sum up all the weighted sum, then you'll get 1. So 1 times 1 plus 0 times -1 plus 0 times -1 plus 1 times 1 plus -1 equals to 1. and then you take the sigmoid. You take the sigmoid of the of it. Now, why do we want to take a sigmoid? Because we know that these values can the weighted sum can go arbitrarily big or small, and then you want to control it between 0 and 1. And in case I have not made it clear yet, the task of the discriminated network is that given this image, given this image, you want to predict the probability that it is a real image. And in this case, the probability is 73%. So the discriminator can say, hey, this is a real face because it's more than 0.5. Now, how would the generator react? So first of all, it wants to predict its first set of images. So what happens is that it will first of all, this generator it will produce not just one image, but a set of many images. So what happens is that it will first choose a random set over here, say z equals to 0.7, and suppose it also wants to restrict its z between 0 and 1. So what happens is that it passes in this it assumes that this neuron has value 0.7, and again this is the bias term, which is 1, and then we have all these connection weights. It will look like a lot of weights. So let me explain to you one by one. So why do we have four neurons over here? Because there are 4 grids that we want to predict, meaning 4 pixels to generate the so-called stunt faces. And then and then how does it get 1.7 minus 1.7 minus 1.7 1.7 over here? So what happens is that so first of all, this is the connection weight, and then this is 0, and then we know that it's 0.7 times 1, which is 0.7. This is 1 times 1 times 1. It is 1, so the total is 1.7. And recall that we want to restrict these values to 0 and 1, and therefore we take the sigmoid. So that this gives us 0.85. If you do the similar thing to the rest, actually I will just show you the other this example, and these two are the same. So the connection weight between this and this is -1. So 0.7 times -1 is minus 0.7. This is 1 times -1 is -1. So the total is minus 1.7. And then we apply the sigmoid, that this gives 0.15. And the rest two are just the same. And by the way, what I said just now is not just something specific about neural networks. Not just something specific about these GANs. It is how neural networks generally work. So yeah, and now that we know how the discriminator predicts the probability that something is real, and how the generator produces its images, we want to look into how they will learn, because if we just know what's the first step, it's not that useful. Like, we want to know how it trains. And recall that both the generators want to know how to improve themselves. And recall, and just a reminder, what is their aims? So the discriminator wants to be better in differentiating. The generator wants to be better in producing fake samples that will look real to the discriminator. So the next thing for this purpose, I'll talk about a bit of terminology. So G means image generated with a fixed Z. So let me go back to talk about what Z is. So here Z is 0.7, and then because we want to generate a set of images, we want to sample Z randomly or according to some distribution, and for each of the Z, we will make these predictions. So yeah, going back to here, so G of Z is the image generated with a fixed Z. So just now this one is G of 0.7, and then D of image is probability that the probability predicted by the discriminator that this I is real. So as a result, we are interested in what D of G of Z is. So the generator wants to fool the discriminator, and therefore it wants the discriminator to think that it's real. So it wants this D of G of Z to be close to 1. and therefore it has this it has this a generative loss, which is called which we denote it as minus ln of d of g of z, and and this thing is zero when this probability is 1, and positive infinity when this is 0. On the other hand, the discriminator wants to be good in this differentiating between fake and real, and therefore it wants to predict the prediction of this fake image to go to close to 0. So 0 means means it's fake, and therefore it has a different loss, which is minus ln of 1 minus this probability. So this one has value 0 when it predicts a 0 probability, and this and value infinity when this is 1. So let's talk about this picture in a more detailed manner. So yeah, this is I would say this is very important. So what happens is that, let's say you let's say this generator, it for one of the sets, it just produces like all four values according to the algorithm that I say just now. And then then after it produces these inputs, the discriminator will pass this input into its neurons and somehow get that this is 0.68. So the next thing what it does, so this discriminator will update its weights according sorry, not update its weights first. It will learn like what is the error function it has, which is minus ln of 1 minus 0.68, because for discriminator, as you can see here, it's 1 minus the minus ln of 1 minus this probability. So this is minus ln of 0.32. And then once it learned this, error function, it will update its weight according to the gradient descent that I tell you just now. So basically, it wants to know like if you change this connection weight by just a little bit, how will this error change? So this is the thing that it is interested in knowing. On the other hand, the generator is also improving itself. So how does it do? So it has so this is the generative loss that is different from the discriminator loss. So here the error is minus ln of 0.68. And again, what it does is that for each of these connection weights, 1, 2, 3, 4, 5, 6, 7, 8, it wants to know like if it increases this weight by just a little bit, how would this probability change? Like how would this d of g of z change when each of these weights increase by a little bit or decrease by a little bit? So this will give d of e, the derivative of e with respect to each of the weights, and these weights will update the weights accordingly. And then the process goes on and on until the generator and discriminator are both very good in their own tasks. So now that we talk about the concept of GANs, let's also review why do we have GANs. So it is partly answered in the motivation behind GAN, but what is the use of it? So the first thing is to artificially create training samples. So when we do training training on neural networks, what happens is that one problem that always comes up is that we want to, let's say, especially in classification, there are just certain classes that are being underrepresented in that sample in that data set. So let me just give you an example. So let's say you want to let's say you want to train a neural network that can detect whether a transaction is fraudulent, and it makes sense to think that, or to infer that the ones that are actually fraudulent is very less compared to the ones that are not fraudulent. So you will end up in a situation where you have this unbalanced data set, and where where you don't have that many fraudulent data. So what could happen is that the neural network, the discriminator, will even though it predicts all the transaction as non-fraudulent, it will still get a very good accuracy score, and therefore it doesn't see a lot of incentives to improve, and we do not want that to happen. The other one is to make neural network more robust towards the corruption that I described just now. So I've just shown you like how powerful how powerful can a perturbation on image on input be, even though the perturbation is very small. So what GAN does is that it will actually train you on on these perturbations, and at the same time, so it will train you on discriminating these perturbations, and at the same time, it will also train you on generating those perturbations. So this will help both parties to improve themselves in a faster way. So one thing about about GAN is that so is it hard to train? Yes, because it has the generator and discriminator have conflicting objectives from in the first place. So one wants to minimize certain error, while the other one wants to minimize the other error, and oftentimes these objectives are not compatible to each other. So what could happen is that your neural network it will be harder to converge. So the one issue that comes up is that when do we stop training? So usually when we train neural networks, that we know we should stop training when we see like, okay, the training loss doesn't decrease much, or maybe the validation loss doesn't decrease much, or even increase. Then we know that, okay, there's the neural network has hit its sweet spot. But it is harder for the case of GANs. The other thing is called mode collapse, because so what happens is that it will the generator will tend to generate only a very small subset of our interested in image space. So yeah, so the final thing I'm showing for this workshop is to show you some application. So the first thing is called this person does not exist, and this is style GAN. Let me show you. Let me see if I can redirect you to. So if you see here, these faces are, according to the researchers, these faces are generated, meaning that they don't. It's not a real person. And if I refresh, yeah, you can see more of this. You can see more of these images on web. Yeah, and then so the underlying mechanism of this style GAN is that it basically find the existing human faces and try to mix the styles of these people. So style means that it means hair, face, facial structure, maybe how the nose looks like, how the mouth looks like, how the ears look like, etc. And then it will just try to mix all these features and produce a new face, a new face. And of course, there are stochastic variations, like for example, like maybe this person's hair is a bit longer and the other is a bit shorter, so it wants to vary by a bit. And the evaluation metric, which is also which could also be used for the training loss. So this one, you don't have to worry too much about this symbol, but it basically just it's a measure on how close are two distributions to each other. So let's say so let's say we assume that both of them are normally distributed, the real image and the generated images. And then we want to compute like basically what's the how far are the mean from each other, and then how far are the variance or the covariance matrix differ from each other. So that's just a measure of distribution similarity. Yeah, I can play to you some of this part of this video. Okay, I think they should they should tell you and at least a bit on how the images are. So the biggest takeaway from this image is that this video is that you can you can vary the features like continuously, and it will somehow go from one spectrum to the other spectrum, where you just generate a bunch of different different type of people. So to make it a bit more to make this a bit more concrete, it means that it means that you basically like mix the different attributes of people, as I described just now. So for example, this is you take this source, the first source, and then the second source. So this one is a lady, and this one is a man with glasses. So what happens that it will produce someone that looks like a man, but with longer hair, for example. And let's take these two examples. So this one, a lady, a woman who is already an adult, and this one is and this one is a kid. So it will produce someone who looks more like a kid, for example. Yeah. The last part of this presentation is yet another example application, which is called cycle GAN. So what happens? Is that you take one image over here, and what you try to do is to let's preserve the background and preserve the shape of the object, but you change you change the color or the or the appearance of this project of this object. So for example, this one it is zebra, but it can go but after this transformation it will become horse, and then you can change it back to zebra again. Same thing, you can from here horse to zebra. You can see that the background is the same, the posture the posture is the same, and here and of course here you see between summer and winter, where you can see that everything does the tree looks the same, but what differs is one side is greener and then the other one has a lot of snow. So yeah, I think that's all my presentation. I'll try to I'll stop the recording for now so that people can ask questions if they want.